Okay, let's dig into a really crucial piece of the modern machine learning world, the feature store architecture.
Mm.
This is so much more than just, picking the right database. It's about building a whole system around this idea of high-speed consistency.
Yeah, consistency is everything. The data has to be accurate, whether you're training a model offline or scoring a live transaction in, what, milliseconds?
Exactly. And let's use a real-world scenario here. Imagine you have this high-pressure task, real-time fraud detection.
The classic example.
Right. A transaction comes in, and you have to score it now. And to do that, you need two very different kinds of information, and you need them instantly.
So you need the real-time stuff, like what has this user been doing in the last minute?
And then you also need the static, pre-computed data, things like their long-term spending habits or, their demographic profile.
And it's that duality, that mix of fresh, real-time data with massive volumes of batch data. That's the fault line. That's where most systems just break.
So what's the first mistake people make? The naive approach.
Well, the most naive approach is just going without a feature store at all. They just try to query their operational databases.
Their main business database.
Their main business database, yeah. They try to fetch the features they need for inference right from there.
And why is that just a disaster waiting to happen?
Because eventually you've got multiple models. Your recommendation engine, your risk model, your fraud detector, they all start hammering that central database at the same time.
Right.
And that sudden heavy load just cripples the operational database. It slows down the main application and, your model's performance tanks.
And even if you could somehow manage that load, you run straight into the killer flaw of MLOps.
The training serving skew.
Exactly.
Precisely. That's where the consistency just fails. If the logic you use to calculate, say, average transaction value over the last 7 days during training is even slightly different from how you calculate it in production,
Your model accuracy just falls off a cliff.
it's gone. The whole point of a feature store is to be that single, consistent source of truth that both training and serving can share.
So the old way, just relying on batch systems where you rerun a job every few hours, that doesn't work either. It's too slow.
No, it doesn't cut it. If your fraud model needs to know a user made a huge purchase 5 seconds ago, a 5-minute batch refresh is useless. You need an architecture that handles both velocity and volume.
So our mission today is to dive deep into that solution, the architecture that can support real-time, low-latency serving, and high-volume batch pre-computation, all while ensuring consistency and scalability.
Right. It all starts with the right path, feature ingestion. A new feature value arrives, maybe from a click or a purchase, and it hits a feature ingestion service through an API gateway.
Okay, and the very next step is almost always a message queue. Why is something like Kafka so critical right there? Why not just write straight to a database?
It's all about decoupling. That's essential for resilience. Kafka acts as a shock absorber.
A buffer.
A durable buffer, yeah. It decouples the ingestion service from all the downstream storage systems. So if your storage layer slows down or, has a problem, Kafka just holds the line and handles traffic spikes and no data gets lost.
Okay, so it's a durable buffer. But when you're designing this for massive scale, there's one design choice you have to make with Kafka that is absolutely critical.
Yes, the partitioning strategy. You have to partition the data based on the entity ID. So user ID, item ID, whatever that core entity is.
So you're grouping all of user X's activity together in one place. Why does that help the read path so much later on?
Because think about it, if you didn't, fetching one user's features for a prediction might mean you have to query, I don't know, dozens of partitions across multiple machines.
A huge fan out.
A huge fan out that just kills your latency budget instantly. By partitioning by entity ID, you know exactly which single partition to look in for all the features for that person. It makes read scalable. From there, the data splits into our 2 parallel streams, online and offline.
Let's follow that online path first. This is the one that's all about speed. Millisecond latency is the goal.
And that kind of speed requires a specific technology. We're talking about a low-latency key-value store, typically Redis or maybe Memcache.
So the real-time pipeline just consumes from Kafka and writes directly there.
Exactly. Key-value stores are perfect because they're not complex. They're just built for incredibly fast lookups with a simple key.
So the goal is hit Redis, get the feature, return it, all within, 10 milliseconds. How do you make sure that even a complex calculation doesn't completely blow that budget?
This is where asynchronous processing comes in. Sometimes calculating a feature takes a while. Maybe you're checking geovelocity or calling an external credit check API. That could take 200 milliseconds.
And you can't have the main prediction service waiting around for that.
No, if you let that computation block the online serving layer, the whole system grinds to a halt. So you have to decouple it. When that initial event comes in, instead of making the real-time pipeline wait, we use another message queue Kafka again, or maybe RabbitMQ. We publish the event to a dedicated queue, and separate computation services pick up those messages when they can.
I see. So they do the heavy lifting in the background.
They do the long-running math, and then they write the final result back to the key value store. This way, the prediction service never waits. It just looks up the most recently computed value that's already there.
That's a great point. You're optimizing the process, not just the storage. So the quick feature is there now, and the complex one will be ready for the next request.
Exactly. Now let's pivot to the other side, the batch pipeline. This is where volume is king, because this is for model training, for deep analysis.
Right. So if the online store is for quick lookups on one ID, the offline store needs to handle huge, sweeping queries across, years of data.
Correct. So we're moving to things built for that kind of scale, like a data lake or a data warehouse. You'll see systems like Hadoop or technologies like Apache Hudi or Iceberg on top of cloud storage. The key difference is the format.
Columnar storage.
Yes, columnar format.
Can you break that down? Why is columnar so much better for machine learning training?
Okay, so imagine you're training a model and you only need 3 features out of 100 for, say, 1 billion users. In a traditional row-based database, the system has to read every single column for every single row. It has to read the 97 columns you don't even need.
Wasting a ton of I/O.
A ton. With columnar storage, you only read the specific columns you actually asked for in your query. It's dramatically faster and cheaper for that kind of analytical work.
So once the raw events are in Kafka, how do you handle the really intense transformations for these batch features?
For that, we rely on powerful distributed computing frameworks. Think Apache Spark or Dask. They're absolutely essential because batch feature generation is so computationally intensive. You're calculating stats, time window aggregations, complex rollups over petabytes of data.
And Spark's whole thing is that it can parallelize that work across a huge cluster of machines.
Precisely. The feature logic is written as a Spark job. Spark reads the raw data, applies those transformations simultaneously across hundreds of nodes, and writes the polished features back to the offline store. Without that parallelism, a feature set could take days instead of hours to generate.
Okay, so we've got our fast serving path, our large-scale training path, and this central definition for consistency. But the moment we add a cache to the serving path to make it even faster, that immediately raises the question of consistency again. Let's dig into advanced caching.
This is where the trade-offs get really interesting and really challenging. For online serving, the cache is there to get our latency down even lower. But the moment you write new data, you have a choice to make.
How important is immediate consistency versus raw write performance?
Exactly. Let's walk through the 2 main write strategies.
Go for it.
First, you have write-through. When an update comes in, the system writes to both the cache and the underlying database at the same time, before it confirms the write is done.
So they're always in sync. Guaranteed consistency.
Guaranteed. But, as you can probably guess, it adds latency to the write. You've got 2 network hops now.
Right. So when would you absolutely need to use that?
For features where consistency is non-negotiable, think of a spending counter in a fraud model. You have to have the absolute latest value right now.
Okay, so what's the alternative? The one that prioritizes speed over everything else.
That would be the write-back strategy. With this one, you update only the cache initially, and then you confirm the write instantly. The update to the actual database is scheduled to happen asynchronously, maybe a few seconds or even minutes later.
Which makes your writes feel incredibly fast.
Dramatically faster because you're only hitting the lightning-fast cache, but you're taking on risk.
The risk being, if that cache server fails before the data is written to the database, you lose the data.
Absolutely. You trade guaranteed durability for speed. You might use this for features where eventual consistency is fine, like updating a user's recently viewed items for a recommendation engine. If you lose a few of those, it's not the end of the world.
So the architectural choice really has to match the business criticality of that specific feature.
100%. And then, once the data is written, you have the problem of invalidation, keeping the cache fresh.
Right.
The simplest way is time to live, or TTL. Entries just expire after, say, an hour. For more precision, you can use event-driven invalidation. A change in a source table triggers an event that explicitly tells the cache to dump that specific key.
Okay, that makes sense.
And for those huge batch feature caches, you might see versioning or just periodic full refreshes to keep them in sync with the massive offline store.
We've put all this work into making our data fast and consistent, but it's all for nothing if the infrastructure itself just melts down under load. So how do we guarantee operational robustness?
This is where infrastructure management becomes paramount. You need a really holistic observability stack. For measuring system health, we start with something like Prometheus.
The time series database.
Right. It collects metrics on everything: CPU usage, network latency, the exact retrieval time for every feature from every component.
And then you visualize that mountain of data with a tool like Grafana to turn the raw numbers into something a human can actually act on.
Correct. And critically, you use those dashboards to define your service level objectives, your SLOs. You set specific targets for latency and availability. If latency goes above your 15 millisecond SLO for more than 5 minutes, an alert fires immediately.
So you're being proactive, not waiting for a customer to complain.
You have to be. And given that workloads are never stable, you have massive traffic spikes. The system has to scale automatically.
So we're talking about container orchestration, something like Kubernetes.
Typically, yes. We'd use something like the Horizontal Pod Autoscaler or HPA, which dynamically changes the number of serving inferences based on real-time metrics like CPU load.
But that's just for the compute side. What about the storage itself?
For the storage, you need horizontal scaling. This brings us back to partitioning, or sharding. We have to shard the data across multiple key-value store nodes, often using a technique called consistent hashing.
Okay.
This ensures that when we add or remove a node from the cluster, we only have to rebalance a small fraction of the data, not the whole thing. And we also use read replicas to offload read traffic and distribute the load.
That sounds like a hugely complex web of microservices. If one feature lookup is slow, how do you even begin to track down where the bottleneck is?
That's the difference between just logging and tracing. Centralized logging with something like the ELK stack is great for seeing what happened on one machine, but distributed tracing using tools like Jaeger or Zipkin gives you the full map.
It follows a single request through its entire journey.
Exactly. From the API gateway, through the ingestion service, to the cache, to the database, and all the way back, measuring the latency at every single hop. It lets you pinpoint those performance hotspots instantly.
And what about preventing a total meltdown? That cascading failure where one slow service brings the whole system down with it.
For that, we use the circuit breaker pattern.
Like a fuse in a house.
Exactly like a fuse. Tools like Hystrix or Resilience4j do this. If the error rate for a service goes above a certain threshold, if it looks unhealthy, the circuit breaker trips. It stops sending requests to that failing service and just returns a default or cached response instead.
Giving the struggling service time to recover.
Right, and preventing the failure from spreading and taking down everything.
So we've built the fortress, we've made it resilient, now we have to govern it. Features are always changing. How do you manage that evolution and ensure reproducibility?
Reproducibility really starts with two things: rigorous versioning and, maybe even more importantly, feature lineage.
Lineage, so tracking the feature's entire life story.
Its whole audit trail, from the raw data source through every single transformation in that Spark job, all the way to the final value that's stored.
Why is that so critical in practice?
Because eventually a model will fail in production and you have to debug why. I remember one case where a model just started making crazy predictions overnight. We used Lineage and found that a totally separate data engineering team had changed the schema of a raw input table.
Oh, wow.
It was a subtle change that broke one of our feature aggregation jobs. Lineage let us find and fix it immediately, instead of spending days debugging blind.
And all of this metadata, the versions, the descriptions, the owners, it all lives in the central catalog, the feature registry.
The registry is the single source of truth for the human side of things. It's the dictionary. It prevents teams from accidentally recreating the same feature or using an outdated one.
Okay, let's wrap up with the security pillars you need to protect what is often really sensitive data.
Security is non-negotiable. It has to be built in from day one. It starts with access control using role-based access control, or RBAC, to restrict who can see what. Not every model needs to see raw PII.
And how do you protect that PII, that personally identifiable information?
Data protection. That means encryption, both at rest on the disk and in transit as it's moving across the network. And for the most sensitive features, we'd use data masking or anonymization, so developers can work with the feature's statistical properties without ever seeing the raw sensitive value.
And of course, the whole system has to comply with regulations like GDPR and CCPA.
Yeah, absolutely.
Wow, that was a really thorough breakdown of an incredibly complex system. So to summarize for everyone listening, you really need 5 core principles for a robust feature store. First, clear data contracts to enforce consistency.
Hmm.
Second, choosing those dual storage technologies, low latency key value for online, columnar lakes for offline. Third, building scalable pipelines with things like Kafka partitioning and Spark. Fourth, designing for resilience with horizontal scaling and circuit breakers. And finally, maintaining operational excellence through really robust monitoring, tracing, and governance.
And, if you tie it all together, this whole architecture is really a balancing act between consistency and performance. And model development cycles are only getting faster. Teams are pushing out new features constantly.
So what's the real future challenge?
I think the real architectural challenge moving forward won't just be about scaling volume or shaving off another millisecond of latency. The ultimate test will be how organizations can maintain perfect feature lineage and rigorous data governance, ensuring every change is trackable while also prioritizing sub-second feature deployment times.
Perfect governance at near-instant speeds. That trade-off is only going to get sharper. Thank you for joining us on this deep dive.